My goal for today, so let's go ahead and start this, is to finish this chapter, and then I want us to discuss the lab. I see an issue right now with this is that you cannot see the words I'm saying because I have this going on. Okay. Anyway, let me minimize this right here. So I want us to talk about the rest of this chapter. So there isn't a whole lot to cover. But then when we're done, I want us to then go over the lab. I don't know how I make this bigger. Okay. You can see my screen, right? This is kind of interesting. Okay. So let's see. Oh, we finished talking about the different graphs, and we're talking about monoproduct, diproduct, and polyproduct acids, right? Sorry, I'm not used to all those words on the right, so I'm getting a little distracted. We'll figure this out. Okay, the last part of this chapter is talking about solubility product. So solubility product has to do with an equilibrium. So it says right here, solubility equilibrium. Remember, chapter 17 is a continuation of equilibrium. So we're seeing equilibrium as it applies to a product, and the product is a solubility product. So the background information here is all insoluble ionic compounds dissolve in water to some degree. So we're talking about insoluble ionic compounds. So let's go back to 1411. Yes, back to the past. In Chem 1411, we talked about soluble and insoluble ionic compounds. Okay? When we were looking at soluble and insoluble ionic compounds, we learned how to distinguish one from the other by looking at the ions in the compound. So, ions in compounds. For example, we learned that all sodium compounds are soluble, all potassium compounds are soluble. So if you have a compound that has sodium in it, it's soluble. If you have a compound that has potassium in it, it's soluble. Essentially, when you look at group 1, you remove hydrogen and you had lithium, sodium, potassium. When any of these ions were part of a compound, their presence alone made the compound soluble. Okay? So we learned all this in 1411. Now in 1412, we're looking at the insoluble ionic compounds. Okay? So do you have to go back to 1411 and review that list? It will help to do so, but I'll show you a way to tell which compound is soluble and which one is insoluble because in my past, when I was doing this, I think in high school level, sometimes freshman level, when I was working on this, I would get anxious and forget which was which. Okay, so I'm going to show you how I survived that. We're told, however, many compounds have such low solubility in water that they are classified as insoluble. So we're saying there are some compounds that are insoluble, right? But we're told that even insoluble compounds have a small degree of solubility. In other words, let me add this down here. There are no 100% insoluble compounds, okay? So what they're saying here, I'm paraphrasing what they're saying. There are no 100% insoluble compounds. Okay? Even insoluble compounds are soluble to a small extent. Okay? So they may be like 1% soluble, but they're slightly soluble, but mostly insoluble. So they're classified as insoluble. Okay? So insoluble compounds, when you're looking at them in solution, they will exist as precipitates. Okay? So they'll be a solid. You will see them as solid. But even though you're seeing them as solid, you understand a small part of it is really dissolved. Okay, let me see here. So knowing that a small part of it is dissolved, we can apply the concept of equilibrium to these salts that are slightly dissolving, and we can use the Ksp equilibrium constant to figure out the relative solubility. Okay, so we'll go into that. So before I continue with the rest of this, get the Ksp, I want to quickly review the Ks we've seen so far. So right here, I'm saying let's review equilibrium constants. Okay, so we started, I know it's been a while since we've been going over equilibrium. We started off with the regular equilibrium. We call this the K equilibrium. This is just a regular equilibrium, right? Standard equilibrium. And then we did the Kc. This one here was equilibrium from concentration. So remember with this one here, to figure out the Kc, they have to give you the concentration of solutions. Okay, then we had Kp. Kp was the equilibrium from partial pressure of gases. Okay, so we talked about K equilibrium. That was just general standard equilibrium. We talked about specifically Kc. Kc usually has, you get the same equilibrium expression, but the numbers you place in those little expressions are concentrations, right? Like molar concentrations. With this one here, it's partial pressure, which may be like atmosphere or any kind of pressure unit, right? And then let me see, what else did we talk about? Oh, we talked about Q. And Q was the reaction quotient. So this is a review, right? Q was a reaction quotient where it had the same equilibrium expression, as in the equation that we wrote was the same, but you used non-equilibrium concentrations or pressure. Okay, so if you've forgotten all of this, just go through your notes and then try to see what I'm talking about. I'm just recapping from the beginning. The first time we ever saw equilibrium and we saw the expression, remember the expression was products over reactants. We've seen different forms of equilibrium, K this, K that. So I'm just going through all the Ks we have seen so far. K equilibrium, Kc, Kp, Q was just the non-equilibrium concentrations or pressures put in the same equilibrium equation. And then we moved beyond that and went into the acid, right? Acid-base chapter, we saw Ka. Ka was acid equilibrium. And then we moved on when we saw Kb. And Kb was base equilibrium. And then I'm trying to think back. We saw Kw. Kw was water equilibrium. So I'm trying to tell you there's so many equilibriums, right? Before we get to the solid equilibrium. So we had K, Ka, Kb, Kw. What was that? There was something else. I just blanked out. Okay, well, this is what we saw before, right? So now we're going to be looking at Ksp. And this is the solid product equilibrium. Okay.
And these are all formulas, right? Formulas.
Right. They're all these are all formulas, right? At the bottom line, all the K, regardless of what's down here, is the product concentration raised to the power of something, whatever x, over the reactant concentration. And remember, these all go with equations, right? So you get your balanced equation. The balanced equation will have the reactant on the left, you will have your equilibrium arrows, and the product on the right. Product on the right. Correct? Oh, I have to talk a little slower. Product on the right. And so your product, even if you have one or two or three, will be on the top. Yes, there are formulas raised to the power, whatever the coefficient is. The reactant will be on the bottom, raised to the power of whatever the coefficient is. Yes, so all of these are equations, and all of these are related to the equations, right? So now that we've seen this, our focus for the end is the salt solubility product. So now we're going to be focusing on this. It will look very similar to the other ones, right?
So with these problems, they'll tell us automatically where when to utilize each one of them.
Okay, so here's the thing. They don't always tell you that. That's why very good question. So what I used to do as a student, because I started realizing what they will and will not give me, ask the same question when you're doing your homework. What do they give you in the homework? Do they tell you it's KSP? Do they tell you it's KW? Right? So as you're working on your homework, have the questions ready. What kind of information will they give me? And then you apply that same information to your exam. If they gave you the KSP in the homework, they will most likely give you the KSP in the exam, right? So I started to tell because we took comprehensive exams. In the comprehensive exam, questions about all these Ks will be in one exam. How do you tell one K from the other? How do you know what K to use? Well, I relied on, for this first one, if I was given a concentration and they asked for Kc, then I knew these went together. Because in my college, the Kc was not given next to the equation. Sometimes you had like a sheet of paper that had all the information you needed. That was tougher because I had to know what information went with what question. So I knew Kc went with concentrations. I knew if I had partial pressure, it went with Kp because the P here stands for partial pressure. Q was not at equilibrium because all the things at equilibrium say K, right? So if the question said non-equilibrium, like this word was in the question, I knew that went with Q because everything that's equilibrium has the K, K, K. I don't know why they didn't use E for equilibrium, but they used K, right? And then if it was equilibrium and it had acid, A went with acid. If it had base, B went with base. If it was water, W went with water. You see, so there are clues into the question so that you don't have to feel lost. And when you're working on your homework, notice that you have an acid equilibrium. Do they give you a Ka? You have a base equilibrium. Do they give you a Kb? They should give you a Kb. What if they give you something else, right? So when you're going into your homework, go in there with a little bit of skepticism of what are they giving me to solve the problem. Okay, so let's go into this part here. So we're told the equilibrium constant for the dissociation of a solid salt into its aqueous ions is called the solubility product constant. So what they're saying is if you're looking at an equilibrium and you're trying to make a judgment of it, if the equilibrium has the following characteristics, this is me paraphrasing. You have a solid salt dissociating, breaking apart into its aqueous ions, you will judge that equation as a solubility product equilibrium. So let me give you guys an example. They use lead 2 chloride. I'll use that. So say you're looking at a balanced equation like this, PbCl2 solid, equilibrium arrows, Pb2 plus aqueous, 2Cl minus aqueous. So you're just looking at this equilibrium equation and you're saying, okay, wait, I know this is equilibrium. How do I know that? The arrow, okay? So you know it's an equilibrium. But you have many to pick from, right? These, how many? One, two, three, four, five, six, seven. You have seven different equilibriums to pick from. Which one is this? Look at the characteristics. Okay, so I'm going to do a little quick check. Does it have an OH minus anywhere in here? No. Therefore, not. Since it's not, so it's not, it's definitely not KB, right? It's not a base equilibrium. Does it have H3O plus? No. The results is not a Ka equilibrium. It's not an acid equilibrium. Do you see the formation of water or ionization of water in here? No. Therefore, it's not Kw. Okay, so you're kind of going through this checkpoint in your head. Since this is missing, it's not a Kb equation. This is missing, it's not a Ka. You're not making water, so it's not a Kw. So these do not apply. But for the Ksp, we're looking for this. Do you see a solid salt? Let me see. Do I see a solid? Yeah, here's a solid. So this is part of my proof. I see a solid. Is a solid decomposing to form ions? Ions are charged particles. They have a charge, plus 2, minus. Yes, I see solid breaking apart to form ions. So, 3 markers. Equilibrium, check. Solid, check. Ions as products, check. So they say here, if you have dissociation breaking down of a solid, check. I forgot. Equilibrium, check. Forming aqueous ions, check. Then this is a Ksp. Okay. So since I've seen that one, this will go with Ksp. So all of these I wrote down here are invalid. Based on that, this is going to be a Ksp equation. Okay. Now that I know that, everything I do just flows from that. So what is our Ksp expression? Just like what we did for all the other Ks, right? Let's find the Ksp expression. In general, K, any K is product concentration. We said that before. Raised to the power of the coefficient, what you use to balance it, right? Divided by the reactant concentration raised to the power of the coefficient. So just like what we did in the beginning, it applies here. We also said for the equilibrium expression, you cannot, so I'll say here, no solids or liquids. Solids or liquids cannot be included in your K expression. It doesn't matter if it's Ksp, Ka, any of those 7 Ks, you can't include a solid or liquid. Okay, so let's write, oh, so before I continue, let's look at our equation. Oh, solid. So we can't use this. This PbCl2 is the compound that's ionizing. We just can't have it in our Ksp expression. Okay? So our Ksp will be our product. Let me zoom out so we can see our product. Pb2 plus raised to the power of, my coefficient here is 1, Cl power of, my coefficient 2. That's it. Right over Pb2, because remember, use a solid equilibrium. So this is it. Ksp expression. One of the goals in there is know how to write Ksp expression like with the ones. Okay. So I'm pretty much right. They give you a generic form, but this generic form very much. I like the example better. I feel like it's more yeah. So first goal met. Next goal is a table. Table of solubility. Let me all K table. So just in general, all K's, I should say I just wrote Ka because I was thinking of writing Ka. So all K's have tables. Okay, there is a huge table online and other places of Kas, different Kas that go with acids. There's a huge table online or in your textbook of Kbs. So all Ks are usually found in a table. So I'm going to tell you this. The K's are very useful information. This K here, the selected solubility product constant. So this is not the whole table that is out there. They have just selected a few compounds here that we're going to be using, right? And these are the compounds. All the salts in here, all of these are insoluble. So this is a list of insoluble salts. Okay. This list is very important. This is one of your survival tools. When they give you this list, they're giving you information about the Ksp that will go with the equation when you ionize this. And I show you how this works. But what they're also giving you that they haven't told you is all of these ions are insoluble. Okay. So if you have a question, is PBS soluble or insoluble? You ask yourself, you're looking at this table, is it in this table? If it is, it's insoluble. Okay. I used this when I was in school. I didn't tell my teachers I was using it. I used it to help me to remember solubility. Okay. So the table goes on. It's not just here. It goes on and on all the way down here. Okay. So before we get into molar solubility, let me show you how this table works and how this plays out. I'm going to, since I started with PBS, I will write an equilibrium for PBS so we can see how this information is useful to us. So I'm going to be working on this part right here. Okay, based on the solubility table, I can write a Ksp, an equilibrium for PBS, where I include the Ksp. Okay, so PBS is a solid, right? Because it appears in this table. I have an equilibrium arrow for it. And then I have to ionize this. When I ionize it, I get Pb2 plus, aqueous, and then S2 minus aqueous. Now, if you've forgotten what ions it forms, this is where you have to go back to 1411. Lead is a transition. It's in the bottom of the P block, but it's transition. It has more than one charge. So you really need to figure out the charge of the nonmetals, sulfur. Sulfur is in group 6. It has a charge of -2. That means for the compound to require one sulfur and one lead, lead has to be +2. Okay? That's where I got these charges for. Sulfur is -2. Therefore, lead has to be +2 for the compound to require one of each because the compound has to be neutral. Okay? So here, so for my equilibrium, oh, I wrote too big. I tend to do this. It's a bad habit. Not really a bad habit. It's a teacher habit. How about that? So my Ksp, I can't write Ka here. I almost wrote Ka. Ksp goes with the solid product, right? Ksp is going to be equal to 9.04 times 10 power negative 29. That's it. This equation goes with that number, okay? And that's how that works. Okay. Now that we've seen all of this, I'm now going to move on to another goal. We've seen how to use the table. I'm moving on to another goal. Our goal here is molar solubility. We need to know how to calculate. So I'm the kind of person, when I'm reading, I'm like, ooh, something new. I have excitement and fear. I have two emotions mixed in there. I'm like, okay, something new. So when I read here, what is molar solubility? They say solubility is the amount of solute, okay, that would dissolve in a given amount of solution at a particular temperature. Wait a minute. This definition is reminding me of molarity because molarity, if I change this word and I put molarity, I'm like, wait, I had to memorize the definition. Molarity is the amount of solute, usually they use the unit moles, that will dissolve in a given amount of solution liters. So even though I'm reading a new terminology, solubility, I'm saying this sounds a lot like molarity. So let's move on. Then they say molar solubility is the number of moles. I'm like, come on, y'all just put that word in there and made it back to molarity. So molar solubility is the number of moles of solute that would dissolve in a liter of solution. So by adding the word molar here, molar solubility, they essentially made this definition molarity. But in this section here, we don't call it molarity because we're dealing with a solid, right? Not a aqueous solution. So it's things like that where I'm like, come on, chemists, come on. Why can't we use the same terminology? It's a different area. Okay. So in this section here, we don't call it molarity. We call it molar solubility because the focus in this section is a solid dissolving, the solubility of a solid. We're judging how soluble the solid is. Ergo, the different definition. Okay? But when it comes to the math, we're pretty much just figuring out the molarity, but we just call it molar solubility. So let's see how it works out. How can we use the Ksp to figure out relative solubility? Okay? So we're told here molar solubility is related to Ksp, but Ksp values of compounds cannot always be compared. And so for Ksp values to be compared, the compounds must have the same dissociation stoichiometry. Okay, what is this trying to say? If we are judging how soluble two compounds are, comma, we can use the Ksp value. That's what I understand when they said molar solubility is related to Ksp. Molar solubility, how soluble is it, is related to the Ksp number. Oh, that's what they mean. If we are judging how soluble two compounds, two compounds are, we can use the Ksp value. Okay? And so they're saying that sometimes maybe the Ksp value may not be available, but we can use the Ksp value. So before we go into more dialogue, why don't we compare two values so we see how that plays out? Um, I will use this number here. Oh, why not? These two, they're next to each other. Uh, it's not always that simple. So let me use these right here. Oh, no, the silver one. Silver one will be better. Sorry. Silver one. Oh, copy. Okay. So I'll use the two silver compounds and then we'll judge which is more soluble. Okay. So we are looking at these two silver compounds, silver bromide, silver iodide. Okay, now I'll tell you why I picked that, okay? Silver bromide, silver iodide. They're simple enough. They're both silver compounds. The question is which is more soluble, okay? So we talked about this in the context of acids, but we're saying here, if the Ksp is larger, the compound is more soluble. Okay? So, if the Ksp is larger, the compound is more soluble. So if you are better with words, you can memorize this and move on with your life, right? I am not. That's not my strength. So for me, I need a logic that will help me so that if you find me in the mall shopping and you ask me, these two compounds, right? Out of context, I'm not thinking chemistry, I'm thinking sale. And you said, I have these two compounds. This is their Ksp value. Which is larger? And how do I answer you on the spot? I need a logic so I can recall, right? So here's the thing. Once again, I picked these compounds because these compounds have a 1-to-1 ratio, one silver for one bromine, one silver for one iodine, right? They said right here, you want to make sure they have the same dissociation stoichiometry, they have the same amounts of the positive and negative ion. It gets more complicated, but yeah, that. So how do I rationalize this? I'm going to talk about this part here because it relates to the chapter, right? Remember we said earlier, Ksp value is product over reactant. Okay? So in your equilibrium, you have the reactant on the left and you have your product on the right. Right? Correct? We also saw the product is the one that's aqueous, the reactant is the one that's solid. So, for the sake of what we're going to be discussing from here on, solid goes with insoluble because the solid will, if you add solid to water, this will be insoluble. Aqueous means has dissolved, right? Therefore, more soluble. Okay. So if it's dealing with solubility or more solubility, we want the right side. If you're dealing with less solubility, we want the less left side, right? So left goes with insoluble, right goes with soluble. Okay, so I'm going to the logical reasoning. Now, we said if Ksp is larger, the salt is more soluble. That's what I said earlier, right? So if Ksp is larger, the salt is more soluble. It leans more to the right. Is that true? Yeah. Soluble is more on the right. If Ksp is larger, that means we also have more product. Ksp is larger, we have more product. So it's product prefer or, yeah, more product. If Ksp is lower, that means we have less product. So we have more soluble product. And this is the logic that helps me remember this. Okay, years from now, I still remember the logic because of this mathematical relationship. If this number is big, the numerator is big, right? Because they're directly related. The denominator is small. So we have more soluble product, less insoluble reactant. So it's just more soluble. The compound is judged by the greater characteristic, right? Okay. So we'll be seeing this over and over throughout this chapter. So we're going to move on right now. We'll come back to that. Calculate the molar solubility from Ksp. And then here we need, we're given PbCl2 in pure water. So I'm going to go ahead and move on with that one. We need the Ksp value. Where's the Ksp? Oh, okay. Let me write this down real quick. 1.43 times 10 power negative 2. Yeah, I'll come back to the conceptual part because we go over that later on. Okay. So for lead 2 chloride, PbCl2, solid, equilibrium arrow Pb2 plus, aqueous plus 2Cl minus aqueous. The Ksp here is 1.43 times 10 power negative 2, right? Okay. We are told to calculate molar solubility, which I'm going to be doing. Okay. In the acid, in the Ka, Kb, in the, what was the other one? In the regular equilibrium, molar solubility that we figured out before, we were just solving for X, right? It was the same thing as solve for X. But in this chapter, since we're dealing with a different class of compound, they don't want to confuse the letters. So instead of saying we're solving for X, we're solving for S. So we're not dealing with X anymore. We're now dealing with S. But it's the same concept, just different formula. We're not solving for molarity. We're solving for molar solubility. Same concept, just applied to a different type or different class of compounds. So again, I will take this part here and I'll make my ice table like I did before. In order for us to solve for, oh, this is messed up. I'll write it over again. Will it let me erase this? No? Okay, let me undo this. Okay, so I'll do this again. PbCl2 solid front and back. Pb2 plus Aq plus 2Cl minus Aq. So if we're asked to solve for S in this chapter, in the previous chapter we were solving for X and we're given a K value, same process. Draw your ice table. Make sure you have your initial concentrations, plug them in here, solve for your equilibrium values, okay? So, did they give me an equilibrium initial concentration of lead 2 chloride? No. This whole question didn't even have a number on it, okay? They didn't have a number because they know you have the Ksp table to get the Ksp. The table is available for you, you can get it there, okay? So I got this from the work they did. You can look at the table. So what I mean here, let me not be lazy because my goal here is to illustrate what to do. Let's see, lead 2 chloride. Wait, am I working on lead 2 chloride or lead something else? Because I'm seeing a different number here. Y'all seeing that? I thought I was working on lead 2 chloride. This is so funny. This is hilarious. I just go with the questions they give me and I copy the numbers from there. Why is the number so different? Oh, sorry. I wrote the answer. That's why you use a table, right? My bad. I just saw this number and I copied it. This is my fault. I should have looked at the table. So the table is 1.17 times 10 power negative 5. See what laziness brings in your life? This is not the actual KSP. The KSP from the table, which is what I should have done instead of being lazy, is this 1.17 times 10 power negative 5. So I should have come here instead of being lazy. This is the number I need. Okay. I just showed you what not to do, instructor. Okay. So 1.17 times 10 power negative 5. That's the number I got from the table. So this is from KSP table. Okay. So they didn't give me a concentration of lead 2 chloride. Does that matter though? It shouldn't matter because since S is a solid, we're not going to be using this column at all. We're not. It won't ever make it into the Ksp expression. Okay. Like before, initial amount of these are both 0 because the product hasn't been made yet. And then change. You look at the coefficient here, this coefficient here, and even though we're writing the change in terms of x, we write the change so it reflects what's happening in stoichiometry, right? Every one of this reacts to produce one of this and two of this. Remember, for the change, if we were including the PbCl2. Oops, what am I doing? Okay, we will say this is minus x, and then whatever this number is will be minus x, right? But remember, we're not using this column at all, so you can ignore that part. But for the product, this would be plus x because it goes with the coefficient. Pretty much take the coefficient and multiply it by x. And this one here will be plus 2x, right? Add up I and C, we get x and then 2x. So now we have our equilibrium concentrations of the ions in terms of x. To solve for, oh, yeah, to solve for x, I just remembered, man, in this chapter, we are using s in the place of x, right? So even though I wrote this as x, I'm going to replace it with S. So it's exactly what we did before, just different letters. So we're not solving for X, we're solving for S. Same like before. I don't know why they switched the letters, but they did. So you recognize how I got it. Same process like before, different letters. So now my K expression, context, KSP. So I write it as KSP. My expression is product ions, so I'm going to put in here Pb2 plus Cl minus, since this is coefficient of 2 squared. Okay. As before, I have to take this number here, 1.17 times 10 power negative 5. 1.17 times 10 power negative 5. That's my Ksp. I got that part. What is this value here at equilibrium? Equilibrium values of this is going to be S. This is 2S squared, so I'm solving for that. Okay, mathematically, this is going to be S, open parentheses here, 2 squared times S squared. 2 squared is 4. S squared times S is S cubed. 1.17 times 10 power negative 5. 1.17 times 10 power negative 5. Okay, now we get to solve for uh, now we get to solve for S. Okay, divide by 4, divide by 4, cancel this out. Let me see, clear. 1.17 exponent. Oh, I didn't use my parentheses. Bad. Open parentheses. 1.17 exponent negative 5 to the right, close parentheses, divided by 4. Okay, so I get 2.925 times 10 power. I don't have a scientific notation here. So hold on a second. Point zero, let's see, 1, 2, 3, 4, 5, 6. Like that. Okay. 2.925 times 10 power negative 6. Okay. And this is going to be S cubed. So what is S? Take the cube root of that. So I'll say power fraction 1/3 to the right, close parentheses. Okay. S is equal to 0.0143 molar. Okay, it's the molar solubility, so the unit looks just like molarity, but the expression, what they call it, is different because it's referring to a different compound. Okay, chemists have a knack of doing that. Same scenario, same experience, it's happened to a different element, it's called something completely different. Okay, so you can write it this way, or scientific notation will be 1.43 times 10 power negative 2, and this is what they had earlier, which I copied as my Ksp value, right? So this shows you how they worked it out and they got the same number, 1.43 times 10 power negative 2. The Ksp came from the table. So when you're working on your homework, if you feel like you're missing something, go to the table and see if that will help you. Okay. We're close to the end. We're not at the end yet, but close to the end. Few slides left. Okay. We talked about common ion, right, when we're dealing with buffers. Now we're seeing a common ion again. Good thing. If you've forgotten it from a buffer, you get to see it again. We have a common ion situation here in our equilibrium. And apparently the common ion is doing something, right? It says here, the effect. So the common ion is doing something to the equilibrium of the common ion on solubility. Okay, so before I go into this, I should have expectation. The presence of a common ion affects solubility. Okay, so now I'm going to read on to see what the effect should be. We're told here, addition of a soluble salt, okay, that contains one of the ions of the insoluble salt decreases the solubility of the insoluble salt. So this is where I was telling y'all about the whole left side is insoluble, right side is soluble. So let me go ahead and examine our same equilibrium, and then we'll see what happens when you add sodium chloride. And I'll tell you a little bit of embarrassing account of my past. It's not really embarrassing. It's not embarrassing to me anymore because it is my past and I've grown since then. When I was working on problems like this in the exam, yes, the exam, okay, I realized during the exam I have forgotten what salt is soluble and what salt is not soluble. and it's on the exam, and I want to get an A. What do I do? I can't ask the teacher. They'll look at me like, what? Right? Okay. So let me work this out and I'll tell you how I figure it out. So when you're working on this, they told you that you are adding sodium chloride to the equilibrium of lead 2 chloride. The salt that has an equilibrium is the insoluble one. So this is what you need to understand. The salt with Ksp value, or and not just any Ksp value, with a small, it has to be really small, a small Ksp value or equilibrium equation is insoluble. Okay? So PbCl2, because they mentioned it has an equilibrium, is the insoluble one. So this one here will have some kind of Ksp value that goes with it, right? And then sodium chloride is soluble. Because they told you back here, you're adding a soluble salt to an insoluble salt. So one, you're going to judge one of these as soluble, the other one as insoluble. Okay. Sodium chloride is soluble. We got it. What does that mean? Let's start with the equilibrium. Pb2Cl, lead 2 chloride, is already at equilibrium, right? Equilibrium is established. Then you go ahead and you add sodium chloride, a soluble salt. What does that do to the equilibrium? It does something, right? So let's see what happens. Sodium chloride is soluble, which means when this gets into water, the sodium will separate completely from the chloride ion. So these ions are now separate, and this compound is not there anymore. They exist as separate ions. They separated in solution. Remember, you have two ions now, sodium chloride, but this whole section is about common ion. So which one of these ions is common to the pre-existing ions? These two are the pre-existing ions. Which one matches? Chlorine, right? So a common ion here is chloride ion. Okay, so what is sodium ion? That's the escort ion, the counter ion. Really not important. So by adding sodium chloride, what we did is add more chloride ion, right? We remember Le Chatelier's principle. Le Chatelier's principle reminds us of how the equilibrium shifts when the concentration of reactant or product changes. Well, we just changed the product, right? So we're going to go to Sir Le Chatelier and say, okay, we just changed the product. We added more product. So now the right side has too much product. It's more heavy, right? So we have increased the amount of product, making the right side heavier. So how does the equilibrium shift to kind of undo the change we made? It has to shift to the left. Because even though I'm drawing the arrow up, what I'm showing you is that we increased. First of all, we had an equilibrium. It was balanced. We added more product, creating an imbalance. How do we go back to the balance? Take some product, add it to the reactant. Oops, I lingered too long. Take some product, convert it to reactant. Man, why is this doing that? Okay. Product, convert to reactant. There. And then restore the balance. Okay. So we had an equilibrium, added too much product, made the product side too heavy. Now we're trying to restore the equilibrium. Take some product, convert it back to a reactant, and it restores the equilibrium. So the reaction will shift left, making some more reactant to restore equilibrium. But remember, I told you the left side is the insoluble side, the right side is the soluble side. So after the equilibrium has adjusted, now we have more insoluble product. So after adding Cl minus, the equilibrium shifts left, comma, increasing sol- um, decreasing solubility. This is how they write it. I know. It's like it shifts left, making more solid, but decreases solubility, which is the same thing as making more solid. Okay. As it makes more solid, it decreases solubility. So in the lab, lead 2 chloride is what color? Yellowish. You will see more of the solid being made. It will look thicker. It will go from being more clear, maybe slightly opaque, and it become more thicker as it makes more solid, decreasing solubility. Okay, you can write it as decreasing solubility or makes more solid. Okay, so let's see. Oh, did they work it out over here? Yeah, addition of chloride ion shifts the equilibrium to the left, and then it decreases solubility, right? So everything I've told you is written here and written here. It's explained here. So hopefully you see that. We're doing another one. Oh, that one was conceptual. This one here is mathematical. So we are told here, what is the molar solubility, which to me is just the molarity, or they're saying here, solve for S, okay, of CaF2 in a solution containing 0.10 m sodium fluoride. Okay, I'll add a page. Okay, so here's the thing. Bottom line, when they say what is molar solubility, what we're trying to do is solve for S, right? Which would be some number. The unit is molarity. Okay, they gave me two compounds, calcium fluoride with no concentration. You notice that there was no concentration. We're trying to solve for that. And sodium fluoride. This one here has a concentration, 0.100 molar. I'm running out of room. Okay. So in the beginning, I was like, okay, the one they gave me the concentration for is the common ion. But let me show you another way of figuring this out. We're looking for calcium fluoride and sodium fluoride. So back to the table. Let's find that table. And let's see what the table provides us. We're looking for calcium fluoride or, oh, there it is, calcium fluoride. Calcium fluoride is 1.46 times 10 power negative 10. Okay, let me write this down here. 1.46 times 10 power negative 10. While I'm here, I want to look for sodium fluoride. So let's pretend I forgot sodium fluoride is soluble because all sodium compounds are soluble. So I've forgotten that, okay? What was that again? Exactly, I've forgotten it. So I'm going to look for sodium fluoride here. Do I see a sodium? Nope. Nope. Down here. Sodium fluoride? Nope. No. Okay. I look for sodium fluoride's Ksp. It's not here. But I did find calcium fluoride. So calcium fluoride is the one that has the equilibrium. Sodium fluoride was added after the fact. You see what I'm doing here? That's how I survived on the exam. I looked at the table my teacher had given me, and I was like, one of these is insoluble. Whichever I find the Ksp for, that's insoluble. So whenever I found it, I'm like, yes, in the exam. And teacher's looking at me. Why is she smiling at me? You don't know. You don't know I'm smiling. Don't worry about it, sir. Don't worry about it. Oh yeah, I enjoyed taking chemistry tests. I was sweating bullets in biology. I was like, what is this? Biology was just a different beast. Because I was like, it could be A, it could be B. And I could argue for either point. Okay, so for my calcium fluoride, what was my number? Ksp is 1.46 times 10 power negative 10. Okay, so I have to write my equilibrium. The equilibrium can only be written for this because it has a Ksp. Ksps go with equilibrium. Ks go with equilibrium. So CaF2 solid arrow Ca2 plus aqueous plus 2F minus aqueous Ksp 1.46 times 10 power negative 10. Okay, so I'm going to write my, I barely have space here, but I'm going to write my ice table here, or draw my ice table. It's hard to draw these straight, but you get the gist of it, right? Okay, so I've used this number. They didn't give me an initial concentration of this. Doesn't matter because I won't be using this column at all because it's a solid, right? Check. Okay, so here's the thing. If I didn't have my common ion, I will put 0 here, and I'll put 0 here, and then I'll continue as usual. Okay? So let me go ahead and continue as usual, and then I'll show you how the common ion influences this. The change in terms of S for this one here is, because it's 1, and this is 1, and this is 2, will be multiply S throughout, then negative for the reactant minus S, plus S, plus 2S, right? And then on the products, on the, what's it called? On the equilibrium, we'll just add these, right? So I want to show you the effect of the common ion. The common ion, kind of like what I showed you guys with the buffer, this common ion affects the equilibrium, no, sorry, the initial concentration of the ion that it matches. Remember, sodium fluoride breaks up into sodium ion, and it also breaks up into fluoride ion. Equal amounts, because you have a stoichiometry of 1 to 1 to 1. That means if we have 0.100 molar of the sodium fluoride, guess how much sodium it makes? Same amount, 0.100. How much fluoride does it make? Same amount, 0.100 molar. Okay, so when this compound, this amount of this compound gets in water, it breaks apart completely to where we have 0 of the reactant. All we have present is the sodium ion and the fluoride ion. Well, both ions don't affect the equilibrium, only the one that's common, right? Only fluoride ion in that amount affects this fluorine amount. So then what does it do to this ice table? Well, change the 0 here and add the amount of fluoride ion. So now you add 0.100 molar because that's the part now that's influenced by fluoride. And then let's see how the fluoride adding to the pre-existing fluoride, like it was a pre-existing condition, right? It adds to that part. And then let's see how it plays out in equilibrium. Okay. Now at equilibrium, add the top and the bottom, we get S. Add this and this, we get 0.100 plus 2S. Just like we did before. Okay? So the part that changed due to the common ion, just the initial concentration of the ion that's common. The other one doesn't change. Okay, we continue with our goal to solve for S, right? Called molar solubility. Okay, let's do this. We're kind of getting close to the end, but I keep adding slides, right? We're still getting close. Okay, to solve for S. Oh, yeah, Ksp expression, Ksp equal Ca F minus squared, right? The 2 goes up here. Oh, yeah, solid doesn't make it. That's my Ksp expression. Okay, I'm going to write my number here. Hold on, let me write this small so I can see all of this. My Ksp value is this value right here, 1.46 times 10 power negative 10 equal, what's my calcium concentration at equilibrium? This one here, S. What's this number here? This. 0.100 plus 2s squared. Okay, I don't know why I wrote that one weird. It's the small things like that. Okay, well, you know how chemists love math, right? I actually think they don't. I think they don't. Okay, because if we leave this like this and we actually work the expression out, or yeah, we'll end up with a quadratic equation. So, to deal with that, what we're going to do is apply the 5% rule. The 5% rule. This is the rule that gets you out of quadratic equation. 5% rule says take the initial concentration provided. Sorry, it's the other way around. It's the Ka over initial concentration. So hold on. It's the K. It was a Ka before. The context here is Ksp over initial concentration. I'll just write initial concentration, right? Ksp divided by initial concentration, multiply it by 100. Do we get less than 5%? Let's see. Our Ksp is 1.46 times 10 power negative 10. Initial concentration is 0.100. Divide that, multiply by 100. What do we get? I can tell you whatever number we get is less than 5%. So 1.46 exponent negative 10. Can you reduce this a little loud? It's not, it's like the frequency of sound. Sorry. My coworker here is having a good time. Okay, times 100. It's a very small number. 1.46 times 10 power 1, 2, 3, 4, 5, 6, 7. Negative 7. Very small. 5% rule passes. What does the 5% rule do to my math? Since you guys are watching this on video, feel free to rewind or pause if you need to do that. I want to erase. I'm not writing a lot of things below here. I applied the 5% rule and it passed. So I'm going to write here, pass 5% rule. What does that mean? After passing 5% rule, I can actually cancel out this 2s. I can make that 0, right? I cannot cancel the s that's multiplied by this because that would just stop the whole work. But I can cancel out the variable being added to a number. And it simplifies my math. Y'all see how simple this is? Right? 1.46 times 10 power negative 10. Now I'm solving for s. 0.100 divided by 0.100. I divide both sides by 0.100. I now have, open parentheses, 1.46 exponent negative 10 to the right, close parentheses, divide by 0.100. And here I have 1.46 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. Could I just do it in my head? Yes. But do I want to do that? No. Why? I'm just being lazy, y'all. There. So this is my molar solubility. Okay. So when you have a common ion, the molar solubility value ends up being very different. It's much smaller because you now end up with more of the insoluble product. So let's go ahead and see how they worked it out. Oh, they started off right here. You see their ice table a lot neater than mine. They don't even bother making one for CAF2 because they notice it's a solid. What's the point? Okay. Oh, okay. I just noticed something. Yeah. That I was like, why is my number slightly different? When I square when I put this 0 here, I forgot this square here. Oh my goodness. Here, that's why I got distracted. I just turned over and talked to my coworker here. I got distracted. This is squared right here. So essentially, this is supposed to be that. That's why I usually have their answers here to double check my work. This is squared, right? I forgot to square this here. So if you're paying attention, go back to that. I forgot to square that. When you square that, it changes the answer here to that. Yeah, just by one number, but it does make a difference in the answer, right? So please do pay attention when you're working. Don't be like me. Pay attention. It was just something small here, but it was significant. This is squared here, so I just forgot to translate that down here, right? So once you work that out, we're done with this part here. Our answers match. Now we're looking at the effect of pH on solubility. Once again, we're very close to the end. What does pH do? So we're told here for insoluble ionic hydroxide, the higher the pH, the lower the solubility of the ionic hydroxide. What does that mean? I know I'm adding a page that makes it longer. If your solid is an insoluble hydroxide, let's see, let's say magnesium hydroxide, okay? And this is your insoluble hydroxide. So I'm going to write out the equation for this magnesium 2 plus hydroxide right here. Okay. So let's say this is your ionic hydroxide right there. If you have a higher pH, what exactly does a higher pH mean? So I'm going to break this down. Higher pH, i.e., greater than 7, means greater OH minus concentration. Okay? When they say high or higher pH, they mean it's implied. A pH that's bigger than 7, because what exactly does higher mean? Bigger than 7. When the pH is bigger than 7, that means it's basic. When it's basic, we tend to have a higher concentration of OH. We learned that in chapter, was it 16? The previous chapter, right? So when you have higher OH and you put this in a solution where you have high OH, it's the same thing. So high pH equal high OH concentration. So what does it do to your equilibrium? The new environment that has a high pH increases the amount of OH present, right? So if you're looking at that beam balance, you now have too much weight on the product side, right? So it creates an imbalance. So you want to bring this back to normal, take some on the right, move it to the left. Convert some product into reactant so that we can get back to equilibrium. So we have too much product, shift some of the product to the reactant, so the equilibrium will shift left. When it shifts left, you have decreased solubility. Why? Solubility, you make more solid. When you make more solid, you have less of the soluble product, so you decrease solubility. So they tell you right here. Yeah. So the higher the pH, the lower the solubility. They say it so casually, like, oh, yeah, you should just know. But I explained to you why that is true. The higher pH means higher OH because it's basic. Higher OH means more product. More product means equilibrium shifts to the left to recreate the reactant. In doing so, the solubility decreases. Also, the lower the pH, the higher the solubility. Higher pH. Oh, this is going back to this part here, right? I don't know. They write weird. Anyway, let me explain the lower pH scenario. Same compound, right? If you have magnesium hydroxide, same situation, solid, which ionizes to magnesium 2 plus AQ plus 2 hydroxides AQ. If you have a lower pH scenario, okay, lower pH, i.e., uh, low pH means, let me stick with the same format, less than 7, right? Your pH is less than 7, i.e., acidic. And acidic means greater H plus concentration. So you add this equilibrium to an environment where you have a bunch of H pluses around here. What does H plus do to OH minus? H plus cannot do anything to Mg2 plus because they're both positive. They can't interact. They'll actually repel each other. But what does H plus do to OH minus? H plus gets with OH minus. There's a bunch of them here, right? And it's like, oh, we get together and they make some water molecule. Yes. So H plus reacts the OH minus out of the equilibrium. So in the process, it will be like H plus decreases the amount of OH minus. Well, what does that do? Back to that visual, right? Imagine you have an equilibrium on the seesaw, but you do something to decrease the weight here. So you decrease the weight moving this up. So now we have this scenario because now we have less weight on the product side. You have less product, less weight. How do you get back to equilibrium? By adding more weight on the product side. You want to shift some from the left to the right. So because we end up with less OH minus because some of it got reacted out with the H plus, the reactant will decompose to replace the lost OH minus. So equilibrium shifts to the right. Okay? When it does so, you have increased solubility. Not all questions will ask you at this level. Some questions will require you to go deep. So be ready to go deep. Okay. They said it here so casually. For insoluble ionic compounds, oh, wait, right here. So yeah, the lower the pH, the higher the solubility. You're free to memorize this and you're free to understand it. Understanding takes more work, but understanding also equips you to answer more questions. When you memorize, you limit yourself to answering very few questions on the exam and on the homework. So let me give you a bottom line that has to do with this. For insoluble ionic compounds that contains anions of weak acid, the lower the pH, the higher the solubility. So we discussed that before, right? So I won't go over that. Before we work on this last problem here, let me give you a summary of what we've seen so far. So quick summary, okay? So summary, okay? With Ksp situations, when you have a compound, let me pick a magnesium hydroxide. Magnesium hydroxide, just because we just talked about it. If you have a solid like this that ionizes to form ions, such as this, or 2Cl minus, right? Okay. We're looking at effect on equilibrium. Okay. Number one, a common ion will shift equilibrium left. Okay. So the common ion here, common ion, I'll put example, anything with a magnesium in it or a chloride in it will shift the equilibrium. Oh my goodness, what am I doing? Sorry, I'm preoccupied because I have an appointment soon, so I'm a little preoccupied here and I'm a little distracted. I get my shot soon, so I'm kind of looking at the time, making sure. Yeah, I am a little distracted. I can tell, it's very obvious. But yeah, so I'm like, why chloride? No, it's supposed to be hydroxide. Sorry about that. I picked this on purpose. So magnesium or hydroxide ion will influence the equilibrium, shifting it to the left, right? So anything you do to increase magnesium, if you have too much magnesium, the response is the reaction shifts left to get rid of the extra magnesium. If you have too much hydroxide, the reaction shifts also to the left to get rid of the extra hydroxide, right? So anything to increase any of these products shifted to the left. In doing so, if it shifts left, you have more solid product, more solid, I just say it that way, more solid, therefore less solubility. Okay. Number two, if pH is high, i.e., greater OH concentration, is the same thing as the scenario here. Greater OH, equilibrium shifts left. If pH is low, i.e., greater H plus, concentration greater H plus reacts with OH minus, decreasing its amount, decreasing its amount. Okay, so H plus reacts OH minus, taking it out of the solution, decreasing its amount. Therefore, reaction shifts to the right. What do we have in the end? Greater solubility. Because the right side is bigger solubility. Okay, more soluble. Okay, sometimes you can remove the compound, any of these ions from here by making a weak acid. So I'm going to add this on the number 4. If ion added produces a weak acid, weak base, or water, comma, solubility increases. Okay, so this will equip us to answer that last question that's coming up. So if the ion added to the equilibrium does any of the following, it makes a weak acid, weak base, or water. These are all compounds that are not easily broken in water. They remain whole. Oops, they remain whole. So weak acid remains whole in water, weak base remains whole in water, water remains whole in water. Solubility will increase. So let me go ahead and work this last question out, and that will help us to wrap up this chapter. Yeah, I'll go over I was ready to go over the lab, but I'll do that later because, as I said, I'm getting ready to go and get a shot. So, the effect of pH on solubility. Determine whether each compound is more soluble in an acidic solution than a neutral solution. So we're going to start. We have a bunch of different compounds. So we have barium fluoride, silver iodide, and then calcium hydroxide. Okay? So I just gave you the rule. If iron produces weak acid, weak base, or water, comma, solubility increases. Okay? So let's see how this plays out. Let me ionize each of these. These are all solids, right? So I'm going to make barium here. See how the question was so simple? They just simply ask you, determine whether each compound is more soluble in acidic solution than in neutral solution. But the process it takes to answer it, you got to go deep. Barium fluoride breaks apart into one barium ion and two fluoride ions. Okay? Check. They said it was in a regular solution. We'll do nothing with that. We'll test out the acidic solution only. Okay. Acidic solution. Acidic, i.e., high H plus concentration. So when they say acidic, they're saying this compound here is placed in an environment that has a lot of H pluses. H plus will go after the negative ion. Now, will H plus react with fluoride? Sure. H plus will react with fluoride ion to make HF. Hmm. Is HF a weak acid, a weak base, or water? HF is definitely not water. It's not H2O, right? It's not a weak base because a weak base is like ammonia or something like that. So it's not this, it's not that. Is it a weak acid? Let's see. So this is me recalling. I know there are six strong acid: HCl, H, HBr, HI, H2SO4, HNO3, HClO4. These are the six strong acids. Okay, any acid that is not in that list is a weak acid. This is an acid, it's not in this list, therefore it's a weak acid. I'm still trying to answer the question, y'all. I'm not done. So since fluorine reacts with hydrogen to make a weak acid, solubility increases. But why does it increase? Because each fluoride that's made will remove each hydrogen that's made will remove a fluoride ion. When you remove a product from an equilibrium, you shift it to the right. Each hydrogen goes in and removes fluorine by making HF. HF doesn't decompose to remake fluoride. HF remains as a whole. And then this happens eventually. Barium fluoride has to make more of the fluorine, and then in the process, solubility increases. Okay, so let me write this out in words. After I've confirmed this, I say solubility increases as hydrogen ion removes H plus, F minus, sorry, F minus from the equilibrium. Okay? So H plus removes F minus. In doing so, solubility increases because the reaction shifts right. Next one we're looking at is AgI. Let me write a little lower here because I feel like it's so crowded up here. AgI. Let me ionize this. This is a solid. Ag plus I minus. Okay, so once again, in the environment where we have a bunch of H pluses, what happens? H plus reacts with I minus to form HI. But wait, I erased that already. Of my list, this is a strong acid. What do we know about strong acids? When strong acids get in water, they break apart to form ions. And for the most part, the ions don't get back together. So once the HI is made, because it's a strong acid, it will immediately separate. They'll be like, wait a minute, I don't want to be with you. The ions will not want to be with each other. They separate. So they get made, they separate. They get made, they separate. In the end, I can say here, no change in solubility, if I can spell. Because even though H can react with I minus, they break apart immediately. They get back together, break apart. They never go off together. So I minus concentration in the solution does not change. Okay? So no change in solubility. Finally, I didn't write the third one. We have calcium hydroxide. Oh, it's right there. And the calcium hydroxide here, also solid, breaking apart into calcium ion plus hydroxide. Okay, the H plus, once again, because all of these are in environments that have low pH, rich in H plus. H plus sees OH and says, oh my goodness, let's form a product. Forms H2O. What happens? Water doesn't just break down. Water, once it's formed, is a stable product. So it goes off. In the process, putting this reaction here in an environment that's acidic, this removes OH minus from the equilibrium. Okay? So when H plus removes OH minus from the equilibrium, what does that do? It increases solubility by shifting this to the right. Okay? So solubility increases as H plus removes OH minus from the solution and the equilibrium, right? So anything that can remove an ion can cause the solubility to increase. Anything that adds the pre-existing ion causes solubility to decrease. Okay? And so essentially when you go through here, they tell you, yeah, this is more soluble because OH is a strong base. If that's sufficient for you and you're able to recall it later, good for you. They tell you here. No, here you have essentially no change, right? Here you have more soluble. So this is greater. Here, no change. This last one is greater. Okay? And so you should have homework questions like this. Once again, the bottom line you're looking for the most part, I'll tell you, you're looking for is a weak acid made or is water made in the environment, acidic or basic water. I mean, in the acidic or basic environment. If a weak acid is made or water is made, then you can conclude solubility will increase. Okay, so they go hand in hand like that. Okay, so yeah, I was gonna go over the lab right now. I won't go over it right now. I will, I'll try to go over it later, depending on how I feel. But if I don't feel too good, I will try to go over it tomorrow. Okay. But Jacob, are you done with the efficacy of antacid lab?
I'm working on that right now. I'm in the middle.
Okay. Okay. So you're still working on the actual lab procedure, right?
Yes, correct.
Okay. So you don't have to do both runs if the first run was done well.
Yeah, I sort of figured that since there was a shortage in the chemicals. So yeah.
Yeah, especially if the first one got messed up, there's no need to do the second one. So what I'm gonna do right now is this. Hold on. What am I doing? Yeah. So yeah, I'll talk about this too, so I can actually record that and do the whole thing together. But yeah, so just work on
Oh,
that.
hey, make sure they remind them to clean the syringe after each time you mix a different chemical. I totally
Right.
forgot to do that, and like I had some changing colors already.
Right, right. They have you they have in a direction clean the syringe. Everything has to be cleaned from one part to the other because
Yeah, it doesn't
you
say it in there.
oh, okay. When I was reading it yesterday, I read the whole thing. Later on, it said clean the syringe. You have to clean the syringe from one, from Let's see. Oh, I'm clicking the wrong thing. Let me show you real quick. The first two parts, what is in the syringe is base. So I guess it didn't say it. Activity one and two. Oh, let me show you the other one. I actually drew pictures and stuff. When I'm reading something that's long, I like to take notes and stuff so I can keep up with it. So I'll go over all of this when I'm actually going over the video. See, I have my little notes over here. Yeah, in the first one, oh,
Is that chapter?
I didn't, huh?
Is that chapter 16?
No, this is your lab.
Hold on, it doesn't look familiar.
Your lab
Oh,
doesn't
yeah,
look
yeah,
like,
yeah. I see it. I see it.
yeah, this is your lab. No, I digress completely into the lab because I was working on this yesterday or the day before. When you and I were talking about the lab, I was working on this. So yeah, in activity one here, this is where they talk about the syringe, right? So in your syringe, what you have in here, this first syringe, activity one, is sodium hydroxide. You have the base, right? In activity one, you have the base in the syringe. And then they probably didn't tell you to change or clean out the syringe from one activity to the other because in activity two, which I have over here
No, I
again.
think
Where
that's I think that's chapter 16 because it talks about the Alka-Seltzer.
yes.
That's chapter
Oh,
16.
oh, sorry. You're talking about what it relates to.
No,
Yes.
no, 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 no. This is chapter 16 PowerPoint that you put up. I was thinking about chapter 17 lab.
Oh, no, 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 I see what you're saying now. Yes, this is a 16 PowerPoint and the lab that goes with that. I see what you're saying. Because I don't normally, yeah, I see. Listen, as far as the order is concerned, I just go, but I separate the lab from the lecture, but I see what you're saying. Yes, this goes with the chapter 16 folder, the second one, right? So with this one here, we have 1 molar of base. So for the second activity, activity 2, in your syringe, once again, you have the base, sodium hydroxide. Right. So if they don't ask you to clean it from the first activity to the second one, that's okay because you have the same compound in that syringe. But in the third activity, right, same compound, sodium hydroxide. Third activity, where I have it somewhere here, here, here they ask you to clean stuff a lot because by the time you get here, I see the picture. Oh, right there. Transfer. Da, da, da. Yeah, number 7. This time you're filling the syringe with acetic acid, different compound. So you have to make sure you clean the syringe. So I see what happened. This third part here, the syringe has acetic acid, which is I abbreviate AC because my teachers did that. Acetic acid. Yeah. So when I'm reading through this is I don't think it's a bad habit in my opinion. Just because I'm able to go through and find things without having to read the whole thing because I spend the time reading the whole thing. So when I'm doing my video, I will use this uh I guess this lab with all the notes on it so you can see the notes I made. It does help me to have a shorthand way of going to find things. I've highlighted all the important stuff and I've, given myself expectations and stuff. Anyways, I'll be doing that later. Later, maybe in the day or tomorrow. Yeah, other than that, that should be good. And I'll be going, I won't do the math with my numbers, but let's see. Are you busy tomorrow, Jacob? That's a very vague question, right?
No, no, I'm not. But
Okay,
hold on. Yeah, I think so. Friday?
yeah, tomorrow's Friday.
Yeah, yeah, I think so.
Okay.
What time are you talking about?
It's kind of contingent upon how, maybe, let's see. Let me make sure I don't have appointments in the morning because, I say yes to all these meetings.
Afternoon is good.
Yeah, let me make sure. Tomorrow is. Oh, tomorrow. Listen, don't worry about it. Tomorrow is actually a holiday, so I don't even worry about it. I'll record it and I'll use made up numbers, which will be completely wrong, but then I'll do the math so y'all can see how it works out.
Okay.
Yeah.
Okay.
So this is it. Oh, we figured out teams. We haven't figured out all our teams. We figured out parts of teams. We got to use that for the first time. So let's see how that works out. Let's see. How do I stop the recording? Stop recording. Yay.
All right. Well, thank you.